Good afternoon, everyone. Thanks again for joining us today. This session is a GCSE Maths session, and it's going to be focused on transformation of curves, part 1. It's going to be delivered by the amazing Molly. As a lot of you already know, Molly is currently studying computer science and maths at the University of Bath, and she's delivered many sessions with us. For new joiners, just to quickly let you know that throughout the session, you can pop any questions you may have within the chat or the Q&A functions. Both are located at the bottom of your screen, and either myself or Molly will get back to you on those questions. This session is an hour in duration, therefore it will be ending at 3 p.m. I think that's all. I'll hand it over to Molly now if she's ready.
Cool. Yeah, I'm ready. Hi everybody, I'm Molly, and I'll be leading today's session on transformations. For those of you who haven't been to one of these sessions before, or for those of you who need a reminder, please pop your questions in the chat or Q&A as we go along, because I check those really regularly throughout. So if it's just a quick, like, I don't get it, can you do another example? Slow down, can you do one like this? I'll answer those as best I can. Or if you pop in some questions that are a bit longer or stuff, I'll come back to them at the end. I always have a 15-minute Q&A at the end of the session. A few people are still joining, but I'll get started anyway, because I think most people are here. Cool. So we've got 2 sessions coming up over the next, so today and tomorrow, about transformations, because I think it's quite a tricky topic. I think it was possibly my least favourite topic in maths. So I'm quite excited to give these because I could definitely have done with them when I was studying maths at GCSE. So today we're going to be learning what the common types of transformation are, what they look like, and how on earth we show them or how we do them. And then I'm going to do like a little introduction as to how we write transformations in terms of a function. So that's scary, like f of x and f of x plus 1 and stuff like that. So I'll be showing, I'll be doing like an introduction as to how we write all of the transformations in terms of this. Don't worry if you have no idea what I'm on about. You will by the end of today. And then tomorrow, we're going to be consolidating all of that, kind of recapping it, and then doing loads and loads of worked examples and word questions and really difficult questions. So we'll get really stuck into kind of the exam prep for it. So I think both lessons will be super useful, and hopefully at least a bit of fun on a gloomy Tuesday. So as I said, whack questions in as we go along. So there are 4 main types of transformation. Now all a transformation is taking an original curve and doing something to it. So you can kind of think about your curve as like a blob of plasticine, right? We can do lots of different things with it. We can, the first one is a reflection. So that means, what does it look like in a mirror? What does our blob of plasticine look like in a mirror? So I'll just do some, I'm going to do some very brief like sketches. So these are not going to be good graphs, but they'll be good sketches. So say we have a curve like, let's say like this, and we want to reflect it. Now, a lot of these have some technical terminology that comes along with them. So in terms of reflection, you have to say about which line or which axis. So here, let's say we want to do a reflection in the y-axis. So reflection in y-axis. So the y-axis is here, and all that means is where are we putting our mirror? So if you put the mirror in the y-axis, what's it going to look like? And what that will look like is this. So we've just reflected it over there. We could also have a reflection in the x-axis. So again, that just means where are we putting our mirror? So let me just do this one in blue. That means we're putting our mirror here. So it means, what would it look like if we popped it there? And it would look like this. So hopefully that kind of make some sense? Oh, someone's told me to slow down a bit, so I will. I've said it before, I talk very quickly naturally, so you're never going to annoy me, just shout at me to slow down. So we imagine putting our mirror here and flipping. So whatever was on the top of it becomes the bottom, whatever's on the bottom becomes the top. So that's what it means by reflection. We can have reflections in other lines. So if someone's asked me to kind of re-explain it, I'll try re-explaining it, showing you maybe some different lines to reflect. I'll try to keep this on the screen in case people are writing it down or whatever. I know I move quite quickly. If you do ever want to go back to something, these are recorded, so you can check afterwards on the My Tutor YouTube channel. You can come back, pause, slow me down to 0.5 times speed, whatever on that. So let's say we have a curve. Let's draw a different one that looks like this. I'm going to attempt to do one now that might go quite wrong, but we'll give it a go. And let's say we want to reflect this around this line. So this is the line, say y equals x. So all that means when you say reflect this curve about y equals x, that's the technical terminology. And all that means is reflect it with y equals x as the mirror. So that means that everything that's on this side flips to the other side of the mirror, and everything that's on this side flips to that side of the mirror. So I'll show you how I would think about doing this. Let's draw our axes and let's put in our mirror. I'd think about it piece by piece as like each side of the mirror. So let's think about this section of the curve. And in fact, I'll color code it for you. So right now I'm just thinking about this bit. Well, it goes kind of from here to here, and it's a curve and it kind of cuts right into that quadrant there. So it's going to look a bit like that. You don't have to be precise with a sketch, which is normally what they're asked to do. Someone said, what about reflection on y-axis? That's like here. The line is here. That's this example. Then I have a look at the next chunk. Well, here the last chunk, which looks like this. So it starts exactly where this one left off, and it kind of comes back to about here, which means it will come to actually here. So that finishing point, we're like reflecting that to the other side. And then it goes like this, just above like there. So then if we join this, if we were to kind of join that up and draw it without all of the color coding, it looks like that. So that's the reflected version of that one. Oh, sorry, about this one reflected on the y-axis, sorry. Let's do that. Let's do that as another example of a reflection. So the question was, we've got this shape, the first one that I drew. Well, not the first one, this one here. And what about if they ask for a reflection on the y-axis? So we put our mirror on the y-axis. And we're going to do exactly what we did before. We're going to look on either side of the y-axis. Let me just box this off so that we know what we're looking at. Draw our axes. Now our mirror is here. Let's look first of all at this chunk. We're just going to flip it over to that chunk. So it's kind of a bit of a half oval type shape. So we just draw our half oval type shape here. And then what's on this side of the mirror? Well, it kind of goes down and then up again. So it starts where this one left up and it goes down and then up again on this side. So we just do down and then up again on this side. So that's what that one looks like reflected in the y-axis. Someone's asked, are you allowed to have a mirror? No, I don't think so. I don't think so. But that's okay, because I promise that if you think about it piece by piece, they're never going to be that difficult. So I'll show you kind of quite a hard one to think about reflecting, and it's going to be actually the same shape that I did before, but let's say we want to reflect it in the x-axis. So here's our mirror. We just have to think about it chunk by chunk. So let's draw that mirror on again. Let's take this chunk first. So we basically look at like underneath. So chunk until it hits there, chunk until it hits the mirror, chunk, chunk. So let's take this first bit here. It goes here and it just goes up to the line. So we just reflect that. So if it's going up to the line like this, reflect it so it goes like this. So you really can kind of visualize a mirror there and think, what would that look like if I reflected it? So that bit kind of goes like that. Now let's think about this bit. It was originally on top of the mirror, so we know it's going to go underneath. It flips to the other side of the mirror. And it's just a curve that cuts through the y-axis kind of at the top. So you're just looking for key elements of it that we can pick out and do. So now we're going to do this curve. But remember, it's been reflected, so it flips to underneath. There we go. Now let's have a look at this little section. This is underneath, just a little curve. So we're going to move it on top. Just a little curve, like that. And then finally, this section is just a line going out like this. So now it's going to go out like this. We're just reflecting that one kind of line bit there. Ooh, that should join up with this. It's quite hard to do. There you go. So this is that curve reflected in the x-axis. Someone said, is it like flipping the quadrants around? Yes, I guess it is actually, because you can kind of see like what's in this quadrant is now in here, but upside down. So I think thinking about it piece by piece really, really helps, because it's, I think, and I'm not a very visual person, so I find it quite hard to immediately get from this to this, but I find it really easy to do it piece by piece because I've practiced it a lot. So you just think about it one bit at a time. Hopefully that makes sense. We'll be coming back and doing more, but I want to get through everything first. Okay, so there's our reflections. Someone's asked, please demonstrate an example of a reflection with a different equation. I will come back to that at the end if we have some time to, because all it is it would just be a slightly different line that's our mirror and we do exactly the same thing. I'll come back to that. Okay, now we're going to think about our second common transformation, which is a rotation. Now, a rotation is turning something around. So if I have my pen like this and I rotate it, that's a rotation, and so on. So with reflection, we had to say which line it was reflecting about. With rotation, we have to say two bits of information. The point that it's being rotated about, which I'll explain what that means, and how many degrees it's being rotated. And which direction as well, actually, but they're kind of tied together, that. So the point that it is rotated about, let's explain it with a bit of a longer pen. So imagine that this is our line, right? If we rotate it about this point, what that means is imagine that you are holding your line, and it's the same when it's a curve, holding it, pinching it at that point, and then rotate it wherever it says that it will be rotated. Because you'll see that if I pinch it in a different position, it will rotate to be a slightly different line. It rotates by the same amount, but see how this one's down here, this one rotates up there. So that's why it's really important. You can also rotate about different points that aren't actually on it. So I could rotate this about this point, and you've just got to imagine it going like that. So this then moves it even further down. And if we rotated it from a point up here, it would do this. You can't even see it. So you've got to imagine that you're either holding it or it's kind of tied to a wire, and you're pinching and rotating it around that point. So that's how I kind of imagine it, I suppose. Yeah, and hopefully it'll make sense as we do some more. So that's the point about which. And then the number of degrees is exactly what it sounds like. So if I rotate this here, so we say about this point. So about this point by 90 degrees this way. So this is, I don't know whether my screen's flipped for you. For me, looking at myself, this is clockwise. Maybe it's not on the screen, but 90 degrees to clockwise, it would go like this. So it's exactly what you kind of think it would be. 90 degrees anti-clockwise, it would go like this. So that's just telling you how much and which way you rotate it. Oh, was that anti-clockwise? Someone said that's anti-clockwise. Okay, that means that I'm flipped for you. I'll keep that in mind. So an example would be, let's take this curve. So this is kind of a sketch of, in fact, I'll do it in a different color so that it stands out a bit. This is a little sketch of y equals minus x squared. It's just a negative, almost dropped my pen, a negative x squared graph. So a negative quadratic, that kind of sad face shape. And say we want to rotate this. Let's see, what could the question be? rotate this curve, and I'll do it about 2 different points so that you can see what I mean. About the origin is kind of examiner's favourite. So rotate this curve about the origin by 90 degrees clockwise. So we can see we've got a lot of information there about the origin, 90 degrees clockwise. So let's see what that gives us. Let's set up our axes. So you've got to imagine now, so the origin, that just means where the axes cross, so this middle point, 0, 0. So where I've done that little pink dot, imagine holding a pin there and turning this round. And what this means, we can kind of again think about this point by point. So if we think about some key points of this, so let's think about the top, kind of the peak of this. That's currently a little bit away from the origin. When we turn it round, it's going to be a little bit away from the origin, but here. So that green dot will go to here, somewhere. It's just a sketch, remember, so it doesn't matter. And then we can think about, I'll do it in dark blue, these dots here, kind of where it crosses the x-axis. Well, now when we turn it, those dots are going to be on the y-axis. So we've turned the whole thing like this, and that means that we're going to end up with a shape a bit like that. Yeah, exactly. So someone said it would be sideways. Yeah, perfect. We've done it by 90 degrees. Now, what if the question was, what if the question was rotate this curve about, oh, this isn't actually y equals minus x squared. This would be more like y equals minus x squared, plus 2. So it actually hits the y-axis at 2. And we'll talk about that in a minute. That's actually a shift. Rotate this curve about the point 0, 2 by 90 degrees clockwise. So it's a really, really similar question. You'll notice that the only thing that's changed is that we're not rotating around the origin, 0, 0. We're now rotating around 0, 2. So we're going to imagine putting our pin here at the top and rotating it around that. Another way of thinking about it is that pin is like the fixed point. So the origin actually wasn't on this curve, but the origin is kind of fixed. It's still in this curve bit. Whereas here, we put the pin here at 0, 2, which is the top of this curve. Then we swing it around and we know that that peak is still going to be there. So what this one looks like is this, because we've kind of put it's a curve like, I think I'm flipped, so it's a curve like this, and we put a pin in the top and swing it around, so that bit that's been pinned there is kind of stuck in that one position, and we're moving. Someone said 90 degrees you move a quarter, 180 degrees you move half, 270 degrees is 3/4, and 360 is all the way back around to original. Yes, that's correct. So that's a good way of thinking about it. Normally, you'll only ever be asked to rotate, especially curves, in either like 90, 180, 270, or 360. You wouldn't be asked like, rotate this 37.2 degrees. That's a bit harsh. So hopefully this makes sense. And we can see that these shapes are actually identical. The reason they're identical is they were both rotated the same amount, but they're in different positions because of which point we rotated it about. So I'd really encourage you to maybe like I was doing with the pen, but maybe cut out a piece of paper in the shape of a curve and try pinning it in different directions. So even if you have a pinboard, that would be a really good thing to do. Literally cut out a curve, stick a pin in different places and swing it by a quarter. And you'll see that it's going to swing in different positions. If we pin it at the top, it swings there. If you pin it on the edge, so if we pinned it down here, it would swing around to be a really low curve down here. So hopefully that makes a little bit of sense. Someone's asked if tracing paper will be provided in the exam. Good question. I do not know. Sorry, because I don't know all the ins and outs of all the exam boards. I can't remember whether I got it or not. I guess for harder questions, potentially, like they'll never ask you something so hard that you need tracing paper and then not give you tracing paper, if that makes sense. So I think yeah, you'll be fine with that. Okay. Oh, someone doesn't understand the 0, 2 part. So all that is it means about the point 0, 2. So you don't need to quite understand why at the moment, but this point on this curve is the point 0, 2, like that point on the y-axis. So what we're doing is like, it's just telling us the point where we stick our pin, basically. Okay, let's move on from that one. Like I said, I can always come back to it at the end if people are still confused. Okay, now we have a translation. So what this means is a shift, a movement. So we take our exact curve. So say this is our line like this. We take it and we shift it somewhere, here or here or here or here or here. We don't change what it looks like at all. We're just moving it to a different position on the graph. And the way that we express this normally is by a vector. So you'll probably have seen a translation of vector 2, 3 or something. So I'll be explaining what that means. Okay. A couple of people said that they were given tracing papers, so they're probably more qualified to answer than me. So there you go. Okay, so let's take a curve. Let's just take a simple, oh, again, I'll do it in a different color. Y equals x squared. Now let's say we were asked to translate this. So our question is, translate this curve by the vector. Now this is, I'm going to have to write out the vector rather than typing it because this is how they're written. Let's do what I said, let's do 2, 3. So this is how they're written. And all this means is 2 right, 3 up. So you've just got to remember that a vector goes right, up. That's what the two numbers mean. So that means that if the top one's a negative, then it means left, because like a negative right is left. That makes sense. If I'm going negative steps in this direction, I'm going backwards. And the same with the bottom one, a negative 3 would mean 3 down. So that's how to read and understand vectors. Someone said, why are the brackets like that? That's how you use vectors. That's just convention, basically. That's just like what the big maths people have decided, you know. That's just how we write them. So what this would then look like is, well, let's just think we have this curve. You can literally imagine like taking this curve, holding it and moving it 1, 2, and then 1, 2, 3. So we'll move it. If we move it 2 right and 3 up, it's going to be kind of here. Again, it's only a sketch. What I would advise is that you then maybe just mark on a key point so that it looks like you haven't, you know, it doesn't look like you've just guessed. So for example, let's take the origin. So y equals x squared goes, the bottom of it's at this point 0, 0. When we've shifted it 2 that way, 2 along the x-axis and 3 up, it actually becomes the point 2, 3 because we've moved it 2 that way. So 2 steps along the corridor and 3 steps up the stairs. So that's just a good way to enhance your sketch and prove that you know what you're on about. Someone's asked to repeat. I'm going to do it again, but with a different curve and a different question. So let's have a look at, let's just say we're given a curve that looks like this, right? Because it doesn't matter what it looks like. And let's say that it crosses the y-axis here. It's got this point, which is 0. It's always going to be 0 because it hasn't moved across the corridor at all. So it's 0, 7. Let's say that's what that point is. And then the question that we're given is translate this curve by the vector, and then I'll fill it in, marking the new coordinates of the y-intercept. So this sounds very confusing, but it's not, honestly. So let's say it's by the vector -4, 1. and we want to mark the coordinates, the new coordinates of the y-intercept. Or I should probably word that a bit better, the new coordinates of the original y-intercept. So basically we want to say, where does this point go to? Well, let's have a look at what would happen to this. Let's fetch this. Now it's going to move -4, so that means 4 places left. Remember, the top one is always left or right, and minus is our left direction. So it moves 4 left and then 1 up. That's exactly what this vector means. So we know that it will like look a bit more like this. Oops. So it will go on up 1 and shift to the left quite a bit, so it looks like that. Now, where's that point 0, 7 gone? Well, it's gone 4 places to the left along with the rest of the curve. So that puts the x value at -4, because it was 0 and now it's gone 4 places to the left. And the y coordinate, well, it's moved up 1. So it was 7 high, it's gone 1 higher. So now that y coordinate is at 8. So the new coordinates of that point, where that point has been moved, is to -4, 8. We've gone 4 left from 0 and 1 up from 7. Hopefully that makes sense. Someone's asked about rotational symmetry. Rotational symmetry basically tells you how many different ways can you rotate something and it look the same as the original one. So it is linked, but I'm not going to cover it in this session. Someone said, is transformations all of the techniques combined together into a question with parts? Yeah, they definitely can be. So that's what I'm going to kind of come to at the end, is we can have a, we can shift something and then rotate it and then reflect it and stuff. And some of these like combine to make other ones, and it can be quite interesting. So we'll have a look. Okay. Hopefully that makes some sort of sense. Again, we'll be coming back to them all. So let's have a look at stretches. This is our final type. So a stretch. So this is where, again, if you imagine your, this is where it helps to imagine your curve as Play-Doh, and we're literally stretching it out either up or outwards. So this is very hard to do with a pen, but say we stretch it this way. That's if you imagine the pen's actually growing. This is a stretch. We could stretch it this way and make it a thicker pen. You could have had a magic pen that did that, but I don't. So I don't really have anything to, I always like demonstrating things. Oh, there is a bit of elastic on my pen. So if you imagine this is an X curve. If we stretch it, it can look like this, or it can look like this. Maybe that makes a bit of sense. I don't know. It might make more sense when I draw it. So we can have, someone said, first of all, someone's asked for another translation example. Yeah, that'll be coming later. Don't worry, I'll do more examples of everything. And someone said, is another name enlargement? Kind of. So enlargement is kind of like a stretch in both directions. So enlargement usually happens, I mean, it can happen to a curve. We normally talk about enlarging, say, a shape. So if you had a box like this and we want to enlarge it by scale factor 3, that means stretch it 3 this way and 3 up. And you've got your new one. So enlargement and stretching are really, really linked. Because I'm talking about it on curves, we talk about stretching. Hope that answers that a bit. So stretches happen in the X or the Y direction. And that just means, are we pulling it out or are we pulling it up? So let's give an example. So let's say we have a curve that looks, these are quite hard to show in a sketch because they could look identical, just the axes would be changed. So I think these, you would almost always get like a point that you need to show. And I think actually my example like video for this lesson that's out there somewhere on YouTube, I think, I do a stretch, which I'll be covering one similar to that, but it's on a sine curve, so I like plot the individual points. But I'll be doing ones like that today, hopefully. So say we have a curve that looks, let's just do this one again, just like a cubic kind of thing. And let's just say, like, we're not told what this is, but we're just told that this point here is just told 2 points. So where it crosses the y-axis is 0, 4. And this minimum point here is going to be 5 minus 2. So we're just told that those 2 points of the curve, and the question is going to be, now there's kind of a keyword that comes in, so stretch this curve with scale factor, I'll be defining that, don't worry, with scale factor 2 in the x direction. So what this means is, well, x direction means we're stretching it out, because we're going, like the other way that they can word this is parallel to the x-axis. It literally just means like do it straight across, like in that x direction. And a scale factor 2 means we make it twice as long. So if I were to do this scale factor 2, I kind of make it twice as long as the original one was. Scale factor 3 is 3 times as long. Scale factor 1/2, it's still called a stretch, but you kind of do it inwards. So scale factor, I want to try to, scale factor 1/2 of this is like, put it off the screen, is we get it from this and we do it to this. You know, you kind of compress it, a compression. So let's do a sketch a bit and then we'll mark on those key points. So as I said, it's actually going to look pretty much identical, but let's just do it for our own benefit. Kind of everything's a bit more stretched out. I just want to make sure that I do everything here right. So can you kind of see what I've done there? Everything's just gone a bit stretched like this. And basically what this means is that, let me just make sure that what I'm saying is right, is that all of our kind of x's have stretched. Just want to make sure I'm kind of saying it right before I tell you everything. So like everything in the y direction has stayed exactly the same, and everything in our x direction has gone like a bit further. It's stretched itself out. So what that means is that all of our x coordinates are being multiplied by 2. That makes sense. It's gone twice as far. Everything is leapt out. That means that this point is still 0, 4. Because 0 times 2 is 0. Even though it's stretched out, it's still along that axis, it's still there. Whereas this point is now 10 minus 2. Remember, its depth hasn't changed, its y value hasn't changed. We stretch something out, nothing gets higher or lower. But the point that was 5, it was 5 across, it's now been stretched out, so now it's 10 across. Hopefully that makes a bit of sense. Someone said, is there a way of remembering everything in maths? Because there's so much to remember. Practice. You've just got to practice enough that everything kind of becomes second nature to you. Past papers, I think, are the best way to remember everything, because yeah, there's no point cramming things. You've just got to do past papers, do enough of it. And once you know how to do maths, it does become quite fun to everyone, I promise. So yeah, hopefully this makes sense, this stretch. I'll give you one more example. So let's say we have, let's give ourselves a quadratic that's here, a little bit shifted. And we're told that this minimum point here is -3, -5. And we want to do stretch this curve by scale factor 1/3 parallel to the y-axis. So I've worded it slightly differently just to get you used to both wordings. So what this means is that it's going to be like 1/3 of the height kind of thing. So everything happens in a third of the space. Obviously these go up to infinity, so they still do, but they happen like 3 times as slowly because everything's been compressed a little bit. So what this means, if we just again do a rough sketch and kind of imagine that, and remember parallel to the y-axis means we're going to do some sort of vertical stretch, so we're stretching it up like this, although it's a third, so in this case it's going in. So it's going to look a bit like this. It's just kind of doing it a bit quicker, if that makes sense. What that means, oh, I know I meant to say, sorry. This should be 1/5. Sorry, just to make my numbers a bit nicer. So it's happening 5 times as quickly. Everything's being squished 5 times. And what that means is at this point here, hopefully you can see it's actually going to be the same as last time. It's affecting the y, so we look at the y, and we just times it by our scale factor. So instead of going down to -5, well, we've squished it, so we've divided it by 5. That's why I wanted it to be that. So this coordinate now is -3, -1. And you can see that makes sense. It comes out the same amount, but instead of going down 5, we've squished it up, so now it only goes down 1. Don't worry if this doesn't make full sense yet. We'll kind of explore it more in today's lesson and tomorrow's. That's why there's 2 sessions on transformations, because they can be super confusing. As I said, they were my least favorite. So all of these, like I said, can be done together. So we can stretch this, we could then rotate the one that we've stretched. So that was a reflection. We could reflect it, we could rotate it, we could then translate it. We can do loads and loads of things to a curve and fiddle it around in loads of different ways. You can imagine if you have like a piece of paper or like a piece of plasticine maybe, like this, you can do whatever you want to it. You can rotate it, move it, stretch it, reflect it, do everything you want to it. So I would encourage you to get a piece of paper or something and kind of fiddle around with it. Just, I don't know, there are probably some websites where you can do that, but they make everything make a bit more sense if you just kind of play around with it. Okay. Someone said they've got a piece of paper. Nice, good plan, because then you can, yeah. Oh, someone said, does Desmos do this stuff? That's a good question. The stuff that I'm about to cover is how you write these in functions. So what we'll do is I'll use Desmos actually. Once I've written everything in functions, I'll show you putting in both of the functions. And then you'll be able to see that it's like a rotated version or a squashed version or something. And someone said, so stretching is multiplying and squashing is dividing. Yes. Cool. So now we're going to introduce something that looks a bit scary. And this is called function notation. Scary words, right? And you've probably seen this before. It's where you have f of x. So say f of x equals x squared. Right? And this looks kind of horrible, right? I think anyway. Well, I don't think so now, but I think that when you first come across it, it looks awful. The good thing is this is super simple. All it is f of x has just replaced y. And the reason is f we call our function. So I imagine f as like a big machine, right? And this tells you several things about it. F is just the name of our machine. We call our machine f. I'm just imagining that it's here, right? What's in the brackets tells you what you give in. And it's normally x. I mean, it won't be like soon because the transformations can affect what you give in as your x, and I'll explain that in a moment. But so you take your x, you feed it into the machine, and your machine gives you x squared. So this means if I have my f machine and I feed it a 4, it spits out a 16. If I feed my f machine a 2, it spits out 4. It's just squaring everything that I feed it. So that's all that it means. It's the same as seeing like y equals x squared, f of x equals x squared. It's just another way of wording it. And I think the best way for you to like learn about that is just by following this and doing loads of different examples with it. Yeah, someone said it's basically maths machinery. Yeah, that's all a function is. It's just a piece of maths machinery that you give something and it gives you something back. So the reason this is fantastic is because we can do function notation, which is the ways that we write what functions are doing. So this is going to be a bit kind of confusing, but I'll show you what I mean. So let's say we have a curve. So I'm going to show you basically what all of the things are. So we're actually not going to do rotation, because rotation you can't really write in a nice way. Not at GCSE level anyway. I don't know when you would do that. But we're going to look at translations, stretches and reflections in terms of just the equations. And what this means is that you can see two equations written down and be like, to get from here to here, I did a stretch of scale factor this. And you can do that by looking at them, which I think is really, really cool. Now, here's what it's going to look like. So we start with our curve. So our original curve is going to be y equals f of x. Now this could be anything. This could be y equals x squared like we had before. Our f of x could represent x cubed minus 7. Our f of x could represent 1 over x. This just means f of y is some function of x, some expression in terms of x, right? Like any curve, like line that you could think of. Really. And then what we're going to come up with is a list of what all of our transformations look like, and like what do they do to this curve. So the first one is, what if we input, instead of giving our machine x, what if we gave it x plus a? So what this means is that we're giving it an extra bit. So instead of feeding it, it's really difficult to explain it. I just kind of want, I know that you'll probably be confused now, but I just kind of want to like give you all of them, and then we'll work through it and understand it. I've only got a few minutes before I open up to questions anyway. So basically, f of x plus a is our way of writing. Won't do equals, do like a little arrow. I'm going to also type this rather than writing it. So this is a translation minus a units in the x direction. I know that this won't be making any sense now unless you've seen it before, so don't worry at all. So what this means is that if we give our function x plus a, if we give it one more than what the point is, this represents the translation of minus a units in x direction. So if we do y equals f of x plus 2, that represents the translation of minus 2. So minus 2 left, minus 2, 0. That vector. I'm just going to write them all down. And if you don't understand, definitely come back tomorrow, because I'll be doing so many questions on it. Then we have y equals f of x plus a. Now what this means is that we give it that, but when it spits us back our answer, it gives us something different. And what you can kind of tell is that because this isn't inside the function, because it isn't attached to the x, this is affecting the y side. So what this tells us is that this is a translation of a units in the y direction. These are kind of things that you do just have to memorize, which is why I hated this, because it's all just different translations and stuff. Then you've got, so those are our kind of translation ones. That's what they look like. What about stretches? So you can, stretches are kind of multiplying by some sort of factor. So what about f equals ax? So we're multiplying our x term here. This correlates to a, sorry, let me just make room that I can actually type this in. This correlates to a a stretch of factor 1 over a in the x direction. So that's just, again, a thing that you have to learn. The x ones always behave weirdly. That's the key thing that I'm kind of going to summarize about this, is that the x is the opposite to what you'd expect. And I'll explain what I mean by that in a moment. Then a similar kind of thing. What if we take that a outside the function? So again, this is affecting not what we put in, but what it spits back out to us. So this is going to give us, again, because it's not in that function, it's affecting what it spits back out, so it affects something on the y-axis. So this is a stretch of scale factor a in the y direction. So this is what I mean by, so with these two, we've got our translations and we've got our stretches. I would really encourage, by the way, writing this down or taking a photo or screenshot of the screen. I'm not quite done, there are two more, but I'll leave it up for a minute once I've done it, because memorize these and come tomorrow to learn how to use them and you'll be totally fine. So this is what I mean by y kind of is more normal than x is. So y, when we are thinking about the y direction, because it's outside of that function, we add a, it's translation of a units. When we multiply it by a, it's a stretch factor of a. However, when we're thinking about the x and we add a, it's translation minus a, like reverses it. When we multiply our x by a, it's a stretch factor of 1 over a. Rather than a, it kind of, again, reverses it. So if you need a way to remember which is which, x behaves weirdly. Then we've just got two more, our reflections. So first of all, this is a reflection in the x-axis. So this is a weird one to think about because that doesn't actually affect the x. So reflection in the x-axis. And this is actually a bit easier to think about. That's because what we're saying is that y is minus whatever you would normally get. So our y value is negative. So if y is 2, it becomes minus 2. If y is 5, it becomes minus 5. And if y is minus 2, it becomes plus 2. So you can see there that that is a reflection in that axis. The other way, and this is what I always think about to tell the difference, so just to write down the other one, that's where the minus is inside. This is a reflection in the y-axis. Because again, this time we're reversing the x's, so it's reflecting over that axis. So here we go. Just while I explain this, write this down, take a photo of it. Remember this. The way that I always think about this is just by thinking about the case of where f of x is x squared. So this you don't have to write down unless you want to. This is just an example. So where y equals x squared. So what y equals minus f of x means, so this first one, that means we take our f of x, which is x squared, and we just make it minus. So y equals minus x squared. Let's just think about these. So y equals x squared looks like this. Y equals minus x squared looks like this. If we do this one, y equals f of minus x, that means you do x squared to minus x. So it's this. So this is the difference. When it's inside the function, you do it to the x rather than like outside the x. And what this looks like, well, that's the same thing as y equals x squared, because if you square something that's negative, it becomes positive. So it's the same thing. And what we can see that this one is a reflection in the x-axis, and this one's a reflection in the y-axis. Again, I know I've gone really quickly, so don't worry if you don't understand. But hopefully you've all had a chance to take a photo, write it down, take a screenshot. Someone said, what's f in the coordinate grid? It's what y is, basically. So it's kind of like f of x. So you put in x on the x-axis and you get out f of x. This is one that's really, really, really hard for me to explain because people understand it so differently. So I would really encourage you before tomorrow to have a go at some questions or like research this, because then you'll come into the lesson understanding a little bit more. Yeah, it's quite difficult to think of. Yeah, so y is kind of this, y equals f of x. Y and f of x are like the same thing. It's what you're doing to your x that you give it. So I know it's kind of, we've only got 10 minutes left, but my plan is to like give you some examples of what these look like, and kind of try to explain this function notation a little bit more. So whilst I'm looking through my questions for that, please do put in the Q&A in the chat any questions that you want me to go over in the last 10 minutes. So this is like a Q&A bit. So ask me anything about, for example, someone said, does this apply to Edexcel, Pearson exam board? Yeah, this content, well, I'm pretty sure that this content should be universal across all the exam boards. Check your specification though. Just check your specification and search for transformations and it will tell you. Yeah, so please do put your questions on now. It can be about stuff that we did at the beginning of the lesson, so on. And that's just while I get up some of these questions that I want to do. Someone's just said, not related to maths, but are you a computer science tutor? Yeah, I do. I currently study computer science and maths, so I do a bit of computer science tutoring, but my speciality is maths. I'm much more comfortable tutoring that. Someone said, sorry, I'll answer this first one. Which year do you learn this? I think I learned it in either year 10 or 11. It's really hard for me to remember which year which stuff happened. They all kind of merge into one. It is a GCSE topic, so around year 10, I think. Somebody said, would this be something you can do without a calculator? Yes, definitely. Because it's just kind of, like the numbers aren't difficult. It's just kind of adding or like subtracting different things or multiplying. Like they're really easy numbers to work with. And someone said, what's our next lesson? The next maths lesson is tomorrow, and it's still on transformations. So we'll be looking a lot more at the function notation, explaining that more and doing a lot of hard questions. Chat, are there any questions? Also, someone said, what should I do with a piece of paper? Cut it into a curve and try different curves, or roll it up and bend it into I don't know. That was just an idea to like play around with it, try rotating it different ways and stuff. Okay. Keep adding questions on while I'm doing this stuff. Please do, so that I know what you want answering. And then I'm going to do these 3 questions, and then one more like what I've done in the example video for this session. And then I will, then we should come to the end. Sorry, brain's malfunctioning today. 2 more questions. Someone said, how many marks would transformation questions be? It depends on the question. And I'll talk about that a lot more tomorrow, because I'll be going over more like exam style questions. So I can tell you this is this many marks, this is this many marks, and so on. Performing a transformation, so just saying reflect this line or so on, will be 1 or 2 marks, maybe a bit more if you have to mark certain points. Questions like this, we have to say describe this transformation, 2 or 3 marks. And some hard questions that we'll be doing tomorrow, 4 or so marks. It really depends on the question. Someone's asked for the name of the graphing website. That's Desmos. And I'll be using that more tomorrow, I would have thought. So DESMOS, Desmos. Okay, cool. So let's have a quick look at these. So these are kind of describing transformations without seeing the curve at all. So what we've got to do is remember, and I'm just going to kind of screenshot what I typed here so that we can have it kind of next to us the whole time. We'll be thinking about it. So eventually we'll kind of memorize these, but for now, absolutely we can have a look at them to check. So for a curve, y equals f of x, so that's always what our like starting curve is. Describe the following transformations. So f of x minus 1. So this means we're feeding it in x minus 1. So when it says, and I'll kind of explain this more tomorrow, but maybe the machine says, okay, give me what you want for x minus 2 and what you want for 2, then we'll give it actually 1. I explained that really badly, actually, and there are probably some better videos that explain it. But in terms of just answering the question, we just refer to these. So let's have a look. Look, it's of this type here. So here our a is replaced by -1. And what does that mean? A translation of minus a units. So minus -1. So that must be a translation of 1 unit in the x direction. So let's put that on. So translation, and we know how to write that. We'll write it in a vector form by vector. So 1 unit in the x direction. What does that mean? That means 1, 0. That's what this one looks like. Let's look at our next one. F of x plus 7. Well, this looks a heck of a lot like this form, doesn't it? But instead of a, we've got 7. So translation, 7 units in the y direction. Brilliant. And we know what that looks like as well. That's a translation of vector, what's 7 units in the y direction? Well, that means a positive 7 units. So we just fill that into our vectors. So 7. Now let's think about this final one. F of x minus 5 plus 2. 2 things are happening to this curve right now. We're subtracting 5 from the x and we're adding 2 to the whole thing. So let's look at it piece by piece. So this x minus 5, well, that's like this. So instead of a, we've got -5. So it's going to translate minus 5 units in the x direction. So that's 5. So we've got 5 units right. And then plus 2. So that looks like this, doesn't it? Because we've got our f of something plus 2, so because it's a plus on the outside. So we're going to translate 2 units in the y direction. So we've got 5 right and 2 up. So let's combine what that means. That's a translation by vector 5, 2. And the reason that we can kind of, yeah, someone got that on the chat, so well done. The reason that we can do this, and I'll talk about this more tomorrow, is because one of these is happening on the x direction, one's happening in the y. So we can actually shift them anyway. We can go 5 up, 5 right, then 2 up, or 2 up, then 5 right, and we'll get to the same point. We'll see tomorrow examples where we can't do them in the same way. So I've just got 2 minutes left, so I'm just going to show you one more kind of type of question that I want to show, and that's this here. For example, so let's put this on. So sometimes you'll get a graph and it will say this is y equals f of x. Sketch the graph of this. So here it says the graph of y equals f of x is plotted. Sketch these graphs. So we're just going to think about this one for now. If you want a harder one, definitely, as I've said before, check out the video that I made for today. That's about sin x. So the way that we do this, got that, is that we are going to, so this is y equals f of x. Let's think about what happens to it and just draw that. And we're going to think about key points. So using what we had before, and I'm going to do this quickly because I'm coming to the end, but what this means is a translation by vector, and it's going to be 7 units right, so 7 in the x direction. So it's translation by vector 7, 0. So what that means is that this point here, this is the only kind of distinct point, well, one of the only ones that we can really see. We know that that base there is then going to be shifted 7, so it goes there. So then how do we sketch this? Well, we can also think about what comes up the top here. So this is just past -6. So we kind of go 7 from here. So 1, 2, 3, 4, 5, 6, 7. So our top point is going to be about here. Like that's where it goes off the screen. So then we can kind of draw that in. And I mean, obviously they're both going to carry up a lot further, but this is what this looks like because we've just shifted it 7 to the right. So the key thing is to work out what on earth the transformation that you're doing is using these function rules and do that. Yes, these are higher tier questions. Someone said they like my hair, thank you. Me too. The next lesson will be a higher kind of lesson. What's the YouTube channel for this website called? I think it's linked like in the emails that you get. I think it's just my tutor, but I can answer that better than I can. And someone's just messaged a joke, so I'm going to finish on that. Why do plants hate maths? Because it gives them square roots. Good one, whoever sent that. And that's everything for today.
That was great. Thank you very much. So the YouTube page is called My Tutor. So you can just type that onto YouTube and you see all the videos that we've got up there. As Molly already said, all of the sessions are recorded, so you can rewatch if necessary. And if you enjoy the session and you're also looking for some more personalized learning, we offer one-on-one tuition, and you can find out more about that on our site as well. So the next session from us is going to be biology, and that's going to be starting at 3:15, so in 15 minutes time. Thank you all for joining us. Have a lovely afternoon, guys. Bye.
Thanks, everybody. Bye.